Okay, so my name's Dave. For the benefit of people next door, this is me. And I work at Halo, which is the taxi app for anyone who hasn't heard of it. And my talk today is entitled Planning to Fail. Being that this is the first talk I've ever done at a PHP conference, there seems to be like a degree of tempting fate in the title. And I did and ah about this title. I considered a kind of less aggressive planning for failure. But then that to me seemed like more of a monitoring talk, reacting to failure. Whereas I'm really going after failure here. I'm actually planning to fail. I'm going to break stuff here. And the aim is by breaking stuff, we can end up with a reliable system, a system that works at scale and that doesn't fail. So that's what my talk is about. But before we get into the details, I'll rewind to the beginning, to where I started out in the PHP world. The wonder of inserting a PHP open tag into an HTML table, directly in some web page, and then getting some stuff from the database. That's the way it used to be done. And my website kind of still does that. It's a little bit more advanced than that, and it runs WordPress. It's arguably over-engineered. It runs on a single VPS. It's a really simple PHP MySQL web app. And my website's quite reliable. I don't actually have any reliability figures. I don't monitor it. If it went down, I probably wouldn't notice. But the Google Analytics traffic seems reasonably kind of stable. So I'll assume that my website is pretty reliable. And part of the reason it's reliable is because it's a very simple website. It doesn't have to do a lot. It could even arguably be simpler. It could probably be static HTML. It doesn't have much growth. You can see the traffic figures are pretty stable. I haven't been slash-dotted recently. There's no enormous spikes. There's nothing out of the ordinary. And there's only one person who ever works in it, and that's me. And I don't work on it very often. So overall, that kind of leads to a nice, stable system. And stable systems are normally reliable. So at Halo, for anyone who doesn't know, it's a taxi app. You press a button on your smartphone, and we'll dispatch a black cab driver in London to come and get you. The company has been around for a while now, just over a year, and it's a company that is experiencing quite large growth. We've just completed our second round of financing, and we've raised $50 million so far. So that kind of gives you some idea as to the scale of the company's ambitions. And that kind of does translate to the tech level as well. It's a reasonably high-volume website. It's not enormous. It's not like Facebook or anything, but we have the app gets a reasonable amount of traffic, and it's quite unreliable traffic. It can be special events like New Year's Eve can catch us off guard. And we haven't had that many New Year's Eves since we've been launched, so we're not really sure what to expect. So there's that kind of degree of the unknown. The functionality seems quite simple on the surface. You press a button, a taxi comes and gets you. But there is quite a lot of complexity there. People, whenever I try and explain what I do to my dad, he's like, so it's just a taxi app. How many people work there? What do you all do? And I'll try and explain what we do and how we build it. But there is quite a lot of functionality there, and there's a lot of engineers working on that functionality. So this is just some stats about Halo and where we're at and where we've been. Halo launched in London. It's a London company in November 2011. And we're now in 5 cities in 3 countries on 2 continents, in the US and Europe. A Halo hail is accepted around the world every 5 seconds. So we've got quite a lot of traction already in quite a short amount of time. And the growth is kind of roughly 30% month on month. So we're getting bigger and bigger. And what does that mean? What does that mean for how Halo operates and Halo's reliability? This is a quote I found in one of the papers from the NoSQL Summer project. I don't know if anyone's familiar with that. It's quite an interesting website, and it was all about getting together and discussing distributed systems. And they've got a list of a load of papers, sort of academic-type papers. And this is from one about harvest and yield. And it brings together 2 ideas, and one of them is from Brooks, and it's saying that the complexity of a software project grows as the square of the number of engineers. And then it brings together a second idea, which is saying that most failures in complex systems are going to result from intra-component bugs rather than, so the kind of, how component A talks to component B, rather than bugs within one component. So the conclusion that this paper makes is that less machinery is quadratically better. So basically, the more stuff you've got, that's not just like a linear, you're not going to have a linear impact. It's actually going to have a quadratic impact on how your system is likely to fail. So at Halo, well, we have a bunch of services. So we have 10 components at the moment, and we're adding more. We run machines on AWS in 3 geographic regions, in 9 availability zones, lots and lots of instances. I think including all of our staging and test ones, we've got a couple of hundred instances. And we've got 10 engineers building the service side of it. So that's ignoring all the app stuff. This is just kind of the back end stuff. And in fact, we're adding people. So if anyone's interested, you can come and grab me later. So what this means is our overall reliability is in danger. This extra complexity and the fact that Halo's got all these engineers, all these moving parts, all this machinery, means that we're going to have to do something to kind of protect our reliability of our overall system. And the coping strategy, one of our coping strategies that we've come up with, is to kind of embrace failure and really take that on. So by doing something a lot, you generally get better at it. So by failing a lot, we can get better at dealing with failure. So this is the Chaos Monkey kind of approach, and I'm sure a lot of people have heard of that. This is a kind of Netflix popularized this idea, which is they've got a sort of daemon that runs during office hours and randomly kills boxes within their live infrastructure. And that's quite a brave approach. We're not quite at that level yet, but it's the same sort of concept. So let's just go back and see how this might impact my website, my reliable website that I run from my single VPC that runs PHP and MySQL. So it is a reliable system, but it's not resilient. My website is not resilient. If I applied the Chaos Monkey approach to my website, it's not going to do me many favors. Any one component I choose to randomly kill is going to make everything stop working. So what we need to do is we need to kind of think about this ahead of time. For my website, this doesn't matter. My website is not a bus timetable app. This is not life and death stuff. So it doesn't matter. No one's going to die. But we do need to choose a stack that's going to work. We need to pick things that are going to react well to this pattern. So what I'd like to do now is talk a little bit about the Halo stack and how we choose technologies that we use at Halo and the sorts of technologies that we're using for different things. This isn't how Halo started out entirely, but it's kind of close. On the PHP side, certainly. There is a lot of Java as well. We had a single box, a bit like my website. So obviously we kind of already getting the hint that this probably isn't all that resilient, which means that it may be reliable, but it's not going to cope well with failure. So we're splitting it up. We're taking the functionality that is Halo, and we're identifying individual services, and we're building out a service-oriented architecture, an SOA. So what that really means is that we end up with lots of chunks of sort of web services, and each one of them does one thing, and it does that one thing well. So one of them might be a service just for storing customer details, and it'll just do that one thing. And the advantage of this is it's a good way of kind of coping with a growing team and a growing complexity and growing number of engineers, because you kind of silo things, and it means that individual services don't change that often. So often, you'll be working on some feature and you won't have to change every single service, you'll just be working on one bit of it. So the rest of it you can just leave, you don't have to deploy or anything, it just stays the same. So we get some advantages from that. So now we've got a service, and this is a service, we've got it running on some box, and it's PHP and it's MySQL again. So we're thinking, well, maybe that's not going to be all that reliable either. So we think, okay, well, we'll put MySQL on a different box. We've got our service, and we can put in place a multi-master replication for MySQL. So now we're kind of getting a bit more resilient. We could now start killing things. Theoretically, if we had two service boxes talking to our multi-master replicated MySQL, we should be able to start killing things without it taking down the entire system. But Halo is a global company, and we're not in London anymore. We're in London. We have launched in Toronto and Boston and Chicago. New York and Tokyo are going to be coming soon. We've already got the data center in Singapore sort of ready for the Tokyo launch. So at this point, MySQL starts to look a little bit less attractive because of the global distribution that we want to achieve. We want you to be able to get on a plane, go on holiday, pull out your Halo app and book a taxi and wherever you land, basically. So what we've been doing is we've been taking the functionality of MySQL and separating it out into the different things that we were using it for. So we were using it for basic CRUD, get me this record, save a record. We were using locking in the form of transactions. So it would surround that with some locking so we could make sure that we were the only person updating something. We were using it for search with things like select star from foo, where X like percent some crazy query. We were using it for analytics, so we were doing select sum this, average the other, group by this. And we were using it for ID generation in the form of the MySQL auto-increment IDs. So MySQL was doing an enormous amount of work for us, and that was absolutely fantastic until you come to try and do that in a way that has a kind of globally distributed system that it's going to be resilient and reliable. So what we're doing is we've kind of, the newer things we're building, we're looking to use other technologies that will do individual tasks well to satisfy those kind of features that we're after. And we're looking for, there's a certain number of things we're looking for, sort of traits that we try and identify when we're picking technologies. And these are kind of the headlines. We're looking for things that are distributed, homogeneous, and resilient. So we're looking for things that naturally run on more than one machine, so that's the distributed bit. We want them all to look the same. We want to be able to deploy some software that runs on 10 nodes, and every single node looks the same. So there's no special masters, there's no special box that you have to kind of protect. We want them all to have the same features, functionality, because that means that when we're operating the software, it makes life a lot easier. It means that the software is more operationally simple. And we want this technologies to be resilient, so we want to be able to kill random boxes. We want it to be able to cope with that and carry on. And this is just kind of to hammer home the point about the kind of homogeneous nodes, this is a quote from Ben Black on his blog, which says, "There is no such thing as standby infrastructure. There is stuff you always use, and the stuff that won't work when you need it." So basically, if anyone's sitting there thinking, yeah, we got a hot spare of that, if this one goes wrong, it's just going to take over all the load, and it's going to work flawlessly. We don't like that pattern at Halo, because generally it doesn't work, and it's quite hard to get right. It's much easier if you've got two of something, and they're both serving half the traffic. Or even better, sort of 3, 4, 5, and they're all serving a fifth or whatever. That's much easier to implement and operate. So these are kind of the headline technologies we've been using at Halo. Cassandra is kind of the backbone in some respects. It's the thing that does all our CRUD. And it has some lovely features, one of which is that operating a single database that spans 3 continents is actually quite easy with Cassandra. You can set it up. It doesn't take long to set it up. Cassandra is probably one of the easiest things we operate in some respects. We've kind of done apt-get install Cassandra on a bunch of boxes, and then we've kind of forgotten about it. We haven't really had too many pain points, or we haven't had to invest an enormous amount of time in getting it running. It just kind of works now in the newer versions. The old versions are a bit crazy. We use Zookeeper, and Zookeeper takes off the job of locking. So if anyone hasn't heard of Zookeeper, Zookeeper is billed as highly reliable distributed coordination. So it's kind of that coordination bit that we're using. So if you want to say, I'm the only one who's going to update this particular thing right now, you need to get coordination. You need to get an agreement from somewhere that that's going to happen. And that's kind of what Zookeeper gives us. There's a lot of kind of well-known patterns that you can implement on top of Zookeeper. Locking is one of them. The other one we use a lot of is leadership election. So if you want one node in a cluster to kind of be the one that's going to say, hey, I'm going to do this particular job, that's another use for Zookeeper. So we use Zookeeper from PHP and Java. We use Elasticsearch to do our search terms. So Cassandra is a fantastic database, but some people who are coming from sort of the MySQL world, MySQL does all these things. It does, if you want to search, you just go, hey, select stuff, where this is like this. With Cassandra, you can't do that. You need to kind of design your queries up front. You need to think about how you're going to want to get the information back that you're putting in. And something like Elasticsearch means that we don't have to worry about building our own search engine. We can just shovel stuff off to Elasticsearch and then query it. It's like a mini search engine. So we've found this to be pretty useful. Elasticsearch isn't on our critical path, though, but it's a tool we use for sort of administrative stuff. We use NSQ, which is a message queue system. And this is something that open sourced by Bitly that's written in Go, and it's a fault-tolerant system with strong message delivery guarantees. So we use this for kind of for our analytics message flow. We use Cruftflake, which is the most rock-solid piece of infrastructure we run. And I think that's probably just due to the name alone. So from now on, we're going to try and call everything with a really crappy name that sounds really unreliable, because then it will just work. And this is kind of a clone of Twitter Snowflake that's written in PHP, and it uses 0MQ socket instead of kind of Thrift-based interface. So it just fit a bit easier with the rest of our stack instead of having to worry about Thrift and running Snowflake. So there's something that all of these things have in common. And it's interesting. They're kind of like, they're not broken by design, which is an interesting point. They're all they all share these same sort of traits. And if you go and investigate how they operate and how they've been designed, you'll find that there's some quite solid things that underpin them. So in Cassandra, which is something I'm sort of most familiar with, I guess, you've got the Amazon Dynamo paper, and that's kind of describes how your data is going to be distributed amongst the cluster, and it describes what kind of queries and consistency you'll be able to get out of Cassandra and how it's going to behave. And it's that kind of fundamental good design that makes life easier for application developers, because when you come to build your app, you don't have to worry too much about this bit of software being flaky. So I guess if there's one take-home message from this talk, it's almost like, if you're going to choose technologies, just think about the design of them and look at how they're being built and what trade-offs have been made by the designers who built them. And ask yourself, are these sane trade-offs? Are these sane design decisions? And that's kind of what's led us to where we are today. So some lessons learned. The first lesson, minimize the critical path. So a lot of applications, and ours is as kind of no exception, has some sort of core functionality that you need to provide. For an e-commerce site, this might be, you need to, the core functionality might be, I can buy something. And then you're sort of asking yourself, well, what do I need to be able to buy something on my e-commerce site? Do I really need to to show the user the top 10 list of things that have been bought on the site today? Is that critical to the functionality of me buying something? Probably not. So what we've tried to do is identify our critical path, and anything that's not 100% essential, we've identified and taken that off. And what that means is we can say, if this thing fails, there will be a degraded performance. You might not get your receipt email immediately, but that's okay because you've still managed to get your taxi. So that's kind of a preferable experience from a user perspective. The core experience is protected, and these extra features are kind of layered on top. In addition to features, there's also the kind of idea of services. So we use Memcache at Halo as well. And when we use Memcache, we've got our own sort of client library. And our client library defers connecting to Memcache until the last possible moment. So we're lazy initializing this. Some people will have an application, and the first thing they do is they have a bootstrap, and the bootstrap will go, connect to MySQL straight away. Let's go and do that right now. And you have to ask yourself, do I need to connect to MySQL right now? Is that something I need to do? Should I defer it to later? By using this kind of lazy init pattern, it means we take Memcache off the critical path for things that don't need it. Not every single request might need it, and the ones that don't just won't connect. And therefore, if it's not working, they won't know. So that's quite a useful pattern. And we need to think about how we configure our clients. So in the instance of Memcache, again, we're going to stick with the Memcache thing, by the way. We're going to go all the way through this. In the instance of memcache, there's a load of options in PHP you can configure. You can set the timeouts. You can define how long it should wait on connection before it gives up. And you don't have to configure these things, but you should. You should go away and configure them. You should look them up and figure out what timeouts am I going to set for this particular client library. And you should repeat this pattern for every single client library you use, be it connecting to MySQL or Cassandra or whatever. Think about the timeouts. And we need to try and pick sane timeouts. So how do we choose a timeout value? What should the timeout be? And what we want to do is we want to base this on data. We want to measure it. So this is from our test cluster, and this is measuring the sort of the mean, which is the blue, the upper 90th, which is the green, and the upper bound, which is the kind of highest value, which is the red. This is the response times from our testing memcache cluster. So you might think, well, we could draw a line there, which is, 20 milliseconds, that's pretty good. That should be our time, that should be our operation timeout. So every operation, if it's longer than that, will say, it's not going to work, give up. Operations never take this long. But we need to be careful. We don't want to set timeouts too tight, because then things will fail that we don't want. And it's a good pattern to just instrument when you decide to give up, so that you've got a measure of that. But also, we don't want to set lax timeouts. A lot of people will have things like MySQL, and they'll have a 30-second timeout on queries. And then most of their queries, they'll take 100 milliseconds, say. And then your 30-second timeout isn't going to do you any favors. Because when things go wrong, what's going to happen is everything's just going to spin, because every process will be waiting 30 seconds, and everything's going to back up, and your PHP FPM or whatever it is that's serving requests, we're all just going to be sat there waiting and waiting and waiting for this thing that's broken. So you need to try and set aggressive timeouts. We'd rather that some component fail quickly, basically. We want it to say, no, I'm broken, please carry on without me. So maybe a better timeout would be there, sort of around the 95th percentile. And we can measure this with data. We can instrument all this in Graphite or whatever, and then make decisions. And then we need to test it. So we need to say, does my configuration work? Does my memcache client that I built, does it work under failure scenarios? What do I want to happen, and does it do it? So this is the kind of thing that we did. We were like, yeah, okay, we want this. We don't want a single box being down to bring everything down. So let's try that. We'll kill it on box A. Yeah, it still works. We'll kill it on box B. Yeah, it still works. At that point we think, yeah, we've got all this covered, we're done. We've solved this problem, which wasn't entirely true. We hadn't solved the problem. Luckily, this was only in our staging cluster, but on one day we realized that our staging cluster was entirely not working. Nothing was returning any responses. So we went and dug into it, and it turns out that one of the Amazon boxes that runs memcache had kind of locked up. And therefore, any of the parts of the application that needed memcache weren't working. And we're thinking, that's really crazy, because we've got all these nice timeouts, and we've configured everything right, we should be there, and it should work, and this is foolproof. But what we've forgotten is that things fail in exotic ways. Things fail in ways that you just don't anticipate. And there are ways that we can model this, and we've come up with some solutions that I'll go through. And in the instance of the memcache, we investigated it. So we started off, we were like, right, we're going to simulate this failure scenario. We're going to find out what is going on, what is broken. So the first thing we did, IP tables, block, reject all traffic. And the expectation is that should kind of work, because the packets are going to get rejected, and the source notified by ICMP, and we expect this to fail fast, and green light, it did fail fast. That's great, this worked. The bits of the application that use memcache just came back and said, no, we're not available, sorry, rather than hanging forever. So we were like, well, what if we just drop the packets silently on the floor, just throw them away? Thank you, throw away. So we set this for test up, and this time we're going to kind of expect the timeouts to be hit. So this is kind of the difference between, if you imagine, when you kill 9 memcache on a box, all the connection opens is going to get rejected. It's like if you telnetted to that socket, it'd go, connection refused, go away. This is kind of the equivalent of, I'm just not playing ball, I'm going to just, I'm not going to tell you. I'm just going to sit here and, not tell you. But that still worked. And then we were like, well, something very strange is going on here. And one of our DevOps guys realized that what was actually happening was that in this particular failure scenario, the Amazon boxes were accepting new connections, even though they were not doing anything useful at all. The box had hung, couldn't SSH into it, took like 10 minutes to reboot via the Amazon console. So they were allowing you to establish a connection, and then they were dropping all the packets on the floor. So, and this, for some reason, was breaking our Memcache client. And lo and behold, it was a bug. There was a bug in the Memcache client, which meant that the connection timeout in this instant wasn't being honored. So this is an interesting one. And this has been quite a useful experience at Halo, just because we've actually found that repeating those kind of tests where we block traffic in different ways kind of really does flush out the clients that don't do what they're supposed to do. And it's a good way of kind of verifying that, if something's not working, it will do what you want it to do, whatever that is. And normally, the worst thing that can ever happen is it just hangs forever. That's normally the last thing you want it to do. So we fixed it, we rinse, repeat. Let's make this, let's fix Memcache. Let's fix that bug, roll a new library. Is it still broken? And that kind of worked. And then we're thinking, wouldn't it be nice if we could kind of automate this process? Wouldn't it be nice if we could know categorically that no change in our system is going to reintroduce that bug? So going back to my website, I never change it. It's very unlikely to go wrong because no one ever changes it. I don't even update the packages. Probably should. But our production environment and our machines at Halo, people are always updating them. There's DevOps team, dev team, people are updating libraries. We've got Puppet that runs. Things are always getting moved on a bit. Little changes. And it would be nice if we could verify that nothing is going to bring back that failure scenario. So automate. That's the next step. And at Halo, we've got a sort of slightly trimmed down version of our infrastructure that we run. We run it purely for automated testing. So it's sat there all day long, powered by JMeter, driving drivers around London, pretend drivers, and they're accepting jobs and doing jobs, putting jobs through. And then what we can do is we can simulate failure. So we can kind of inject cases, and we can say, right, go and enact the Memcache failure, and then assert that it does what we want it to do. So this was actually our first attempt at fixing the Memcache problem. So you can see we've got this thing called timed block. Timed block is just a little shell script that someone wrote which just did the IP table stuff. So you can see when we start the time block, the responses suddenly jump, and this is the sort of JMeter output. You can see it so we're suddenly adding kind of 500 milliseconds, and we're thinking, that's not what we want to happen. This is not the desired behavior. And this is because we hadn't covered off the point I mentioned earlier, which is choose sensible timeouts. We'd chosen ridiculous timeouts. We'd chosen sort of a half a second Memcache timeout when every operation was, when every operation completed in less than 20 milliseconds, forever. And we'd chosen 10 times that as our timeout. So we fixed that, and then bingo, this is what we want. So now, when the customer logs in, they don't notice. Memcache is failing in this exotic way that previously brought down everything, and now it works. And we can run this every night. So every single night, this goes off, runs, asserts that it does what we expect it to do. So that's our kind of automated testing framework. And we can also simulate these in tests as well. So this is another thing that we've kind of taken to doing, which is that we write system tests for our software that kind of asserts what we want to happen. And this is a kind of another good exercise, because most people will write software and they'll just follow the positive use case. They'll write their code, it works, let's not consider what happens when things go wrong. Whereas what we do in the system test is we say, right, if this component is failing, then we want this outcome, whatever that outcome is. It's really up to you. So this is an example of one of our system tests where we are simulating Memcache failing. And then we can assert that our monitoring should pick this up. And then we can assert that features will still work. And this is just kind of a markdown file that we can execute. So this is just basically doing REST calls. It's kind of system tests as markdown. But the key idea is we are defining what we want the behavior to be, and I think that's an important point. We're not just leaving it unspecified. So, finally, to conclude shortly, the best way to avoid failure is to fail constantly. So this is really the key take-home. If you want to get good at something, you do it a lot. If you want to get good at dealing with failure in a system that runs on 3 continents, on 200 machines, you just need to fail a lot. And you need to automate that. And you need to make sure that you're asserting the behavior that you want to happen. And that you really need to automate that. Because before we automated it, we would do the pattern where every 3 or 4 months you'd go and investigate and you'd try out some failure and see what happens. But for the next 3 months, no one's repeating that process. You're just getting on with your other work that you've got to get on with. Whereas if you automate it, it just happens every night. These failure scenarios play out. You see what the results are. Someone can come in, look at a graph, go, oh, hang on a minute. That thing that you committed last week, that really does mess with our failure handling. Please have a look at that. And then off the back of our success with the timed block all the things. So go away and see how your application fails when you kind of disrupt the flow of the traffic to different components. Find out what do you want the desired behavior to be, and find out what the behavior is, and then adjust and correct. And we found that the IP table stuff was like a really quick way of doing this, and we found quite a lot of bugs, or a lot of sort of shortfalls in other software and other packages just by following that kind of process. So that's my talk. Thank you. And there are some references for this sort of further reading on the slide deck that you can check out later. So any questions?
Are there any questions in this room or on the other room you would like to ask Dave?
That must have been clear.
Over there.
Hi.
Hi.
So you said you've got about 10 plus services. And how do you test the integration between these services? Automate it in any way? Or?
Yeah, so the way we test the integration between all the components is ultimately to test it end to end with pretend drivers and pretend jobs. So we use JMeter, which is kind of a Java app for load testing, but it's very, very flexible and it's really extensible. So we've basically built this app in such a way that we kind of extended it so that it can simulate a driver driving around London and accepting job offers and then doing jobs. So what we do is, there's kind of 2 parts to it. First of all, there's driving traffic through it, and then there's obviously monitoring what the results of that are. And we monitor the results in 2 ways. The first is this kind of JMeter response. So JMeter will record, what percentage of requests failed, what your mean and response time is, what your, the sort of standard deviation, all that sort of stuff. And we also make heavy use of graphite. So we basically instrument everything. And then in that way, you kind of get an easy visual picture of what your performance characteristic of your application looks like. And when you push out new code, you can kind of draw bars and say deployed done here, and you can kind of see. So in terms of testing integration, we really do, the kind of ultimate end game is to test it by actually simulating what real people do. And we find that that's kind of the most effective. And the next step that a bunch of people are working on is actually doing that from apps. So we've got a couple of guys working on a kind of system that is going to actually press buttons on apps to do these tasks. And you can, I don't know all the tech around that, but basically it kind of runs our actual app code and then simulates a hand moving and pressing a button. And that's kind of a really end-to-end way of doing it, because that is the actual apps doing it. So that kind of is useful in that it asserts how the apps behave, and sometimes they do crazy things.
So the test environment that you run, that's constantly simulating, do you try out your deployments and try failed deployments as well?
Yeah, for sure. We everything that we release will get pushed through that environment. One of the features that I've been working on recently, which is swapping in a sort of swapping out an old piece of functionality for a new service, had a sort of vaguely involved upgrade path. So we tested out all sorts of scenarios of, rolling it forward, rolling it back. What happens to the user experience? Can people who are using the app within that time carry on doing their journeys? So we can test all that stuff out. And the aim, the ultimate aim really is that if I push code, if I introduce some new feature, what we really want to be able to do is assert that the kind of overall performance character of the entire app, the entire sort of user experience isn't impacted too much. So if I accidentally introduce an extra second on login, that should be a graph going, whoa, what have you done, Dave? Undo that. That's kind of the aim. Yeah.
What was the migration from MySQL to Cassandra like, or was it at a sufficiently early enough stage that it was fairly easy to kind of make the switch?
Yeah, so the beginning of the question was, what was the migration from MySQL to Cassandra like? Quite easy, I guess. I mean, it wasn't just about migrating from MySQL to Cassandra. It was more about, we're going to replace this particular function within this kind of web app that runs on a few boxes in one location, and we're going to replace that with a service that runs globally and can be accessed from Tokyo, New York, whatever. So it can, to some extent, there is a degree of scariness. But in terms of the actual, moving from MySQL to Cassandra, not really. Not that bit of it is probably like the least scary bit. I guess the difficulty with apps, to some extent, is that our application has to do what it did yesterday because the apps can't change. And if we introduce something that means that if we start behaving differently, there's every possibility that they'll break. And then with Apple, it's like 2 weeks to get a fix out. So we just have to be a bit careful there, but not all that difficult.
Could you place an estimate on sort of how much development time you dedicate towards these sorts of tests and testing to fail versus actual development time moving your application forward, and what penalty that has in a business sense? Like, how did you guys go through that decision-making process? Are you still in the venture capital stage of your business, or are you actually using your own revenue to fund these sorts of changes? Because it will make a difference, when you're talking about, making your business viable.
Yeah, so that's quite a good question. So yeah, we're at the venture capital stage. We've raised quite a lot of money, and the business is all about growth. So we've got one guy who works full-time on automated testing out of an engineering team of 30 maybe. So it's not an enormous amount, and it's surprising how much you can actually achieve with that. And I think the key is to automate it. If you invest, some of the things we've done, you could sit down in an afternoon and achieve, but then once you've done it, you're kind of throwing away that work. Whereas if you can spend 3 days and set up, just something that does it every day or regularly, then you've kind of gained quite a lot, because you can then just leave it alone and it will go away and do that. And actually, I think it's a very important thing for us to do, the automated testing, the failure scenarios especially, because we want to make a lot of changes to the application. And the only real way of being able to do that is to know that you haven't broken it. And the best way of knowing you haven't broken it is to have all these tests. So in that respect, I think it definitely pays off.
Hi. I was just wondering, do you ever do sort of test-driven development with infrastructure? So sort of you've got a service that performs at a certain level and you want to decrease that, say, by 200 milliseconds, but you don't know how to do it. Do you ever sort of look at a problem that way and then investigate how you might be able to get down to that?
Yeah, that's an interesting sort of approach. We haven't really done that. So I guess that's sort of looking at it from a performance perspective. At the moment, our main focus is really on kind of just building the core functionality in nice units that are maintainable. But I think that sounds like a really good approach. I'd be quite up for doing that. I like the idea of having that kind of what do I want to achieve up front, and then going about sort of measuring it and saying, have I done it? And if you could automate that, that'd be good. Yeah. So no, we don't do that, but it'd be nice. Sounds nice. Okay. Go on.
How do you have an idea of when you've How do you have an idea of when you've covered off all of the failure scenarios? Because there are many, and thinking about what.
Yeah, that's a good question. So, how do we know? How do we know when we've got it all covered? I guess we don't really, but we know what components we use. We know what technologies we are using, and most technologies come down to some network socket that you're talking over. So from that perspective, it's not actually that time consuming just to exhaustively test them all. So that's kind of what we're aiming to do. But yeah, I guess I don't know how we'd know that we've definitely covered them all. I guess you learn every now and again. You have an outage and you're like, should have thought of that. So we're trying to kind of avoid that as much as possible. Okay, well, you can always grab me after if anyone wants to chat. Thanks very much.